in this video we're going to discuss power series, what they are, how to find their radius of convergence, and interval of convergence. So first things first, what is a power series? Well, a power series is a special series that has the following form. It can be written as the sum, n equals 0 to infinity, of c sub n times x minus a to the n. So you could think of it as if c sub n is sort of like what our a sub n used to be when we were just looking at plain infinite series. And then now there's this extra term x minus a raised to the nth power. Well, what does that look like if we expanded or wrote out the first few terms of this sum? Well, if n is 0, I'd have c sub 0, and then x minus a to the 0, so that would just be 1. So the first term would be a constant. Then the next term, I'd add to that c sub 1 times x minus a to the first plus c sub 2 times x minus a squared, and this goes on forever. Now, this is equal to a function, right, f of x, whose domain would be the set of x values for which the series, and we say that this series is centered at a, converges. So it's only a function provided you're plugging in values for x that allow the infinite series to converge. All right, now there's three possibilities. The first one is that there's a set of values, part of the radius of convergence, that comprise the interval of convergence for which this power series will converge. So as long as you substitute in a value for x such that x minus a is less than r, then we say that this infinite series will converge. The next case is the infinite series only converges if x is equal to a. And you could see, of course, it would converge if x equals a, because you're plugging in a minus a, which is 0, to the n for every single term. So basically all of the terms are just 0 added to itself. So sure, it's going to converge. In that case, we would say the radius of convergence is just equal to 0, and the interval of convergence just is a set containing the value a. Okay, it's not an interval, it's just one value by itself. And then the last situation is that x can be any real number and the power series will converge. So then your radius of convergence is infinite in size, and the interval of convergence would be all real numbers. So the interval from negative infinity to infinity. Okay? So when you're working through and trying to find the radius of convergence for infinite series, you're either going to use the ratio test or the root test. Okay? So let's look at an example and dive right in. First, we're going to find the radius of convergence and the interval of convergence for the following series. So we have the sum n equals 0 to infinity, negative 1 to the n, times x to the n over n plus 1. All right, so it looks like a good time. Let's just use the ratio test. And so we have the limit as n approaches infinity of the absolute value of a sub n plus 1, so that's going to be negative 1 to the n plus 1 times x to the n plus 1 over n plus 1 over a sub n, so that's negative 1 to the n, x to the n over n plus 1. All right, so when I take this absolute value, negative 1 to the n plus 1, negative 1 to the n, that's all gone. So I have the limit as n approaches infinity. Now I still need absolute value because remember, x can be any real number. So I know n isn't going to be negative, but I need to keep the absolute value around x. I'm going to split up x to the n plus 1 into x to the n times x to the first over n plus 1, that's n plus 2, times, and then now in the numerator, I'm going to have n plus 1, and then just x to the n in the denominator here. Okay, looks nice. So let's see, what can we do to clean things up? I can cancel out this x to the n, and then now I have the limit as n approaches infinity of the absolute value of x times n plus 1 over n plus 2. All right. Now I can split up the absolute value and write this as the product of the absolute value of x times the absolute value of n plus 1 over n plus 2. Now look very carefully at this limit. This is a limit as n is approaching infinity. So x is a constant in this limit. X is a variable, but in the limit, it's not changing. So I can pull absolute value of x outside the limit. So I can write this as the absolute value of x times the limit as n approaches infinity. And I don't need absolute value around the n portion, so I have n plus 1 over n plus 2. Now as n approaches infinity, degree of the numerator is the same as the degree in the denominator. So this portion is just going to approach 1. So this limit is equal to the absolute value of x times 1, which is just absolute value of x. Now, in order for this infinite series to converge by the ratio test, this limit needs to be strictly less than 1. So basically, we are imposing this condition. We are requiring that the absolute value of x be less than 1 in order for the power series to converge. So you have to know the statement of the ratio test to know that we want to impose that condition. Okay, so what does this mean for us? Well, that means that the radius of convergence is equal to 1. So the radius of convergence which you can just write r, is equal to 1, okay? Third time was a charm. Okay, so whatever this value comes out to be here, right? Sometimes you might have an extra constant, so it won't always be exactly 1. Now, what is the interval of convergence? Well, look back here. This infinite series is centered at 0. So this is centered at a equals 0. How do I know that? Because it's x minus 0 to the n. That's a. All right, so it's centered at 0. The radius of convergence is equal to 1. So I have 4 options for my interval of convergence. It could not include the endpoints at -1 and 1. Or it could include just one endpoint. It could include -1. Or it could include +1. Or it could include both. In order to determine which of those 4 cases we have, then I'm going to test each of the endpoints. I have to test at x equals -1 and x equals +1. So let's start off by testing x equals -1. So I'm going to let x equal -1. And remember, our original series was the sum n equals 0 to infinity of -1 to the n times x to the n over n plus 1. So if I substitute in -1 for x, now I'm going to have the sum n equals 0 to infinity of -1 to the n times -1 to the n over n plus 1. And then that means in the numerator, I'm going to have -1 to the n times -1 to the n. So that's -1 to the 2n, n plus n. So that's always going to be even. So now I'm going to have the sum n equals 0 to infinity. I can just write this as 1 over n plus 1. All right, now if you are pretty slick with working with series, you might notice we can shift our indices and basically be done. So instead of starting my series at 0, I can actually start it at 1 instead. I'd still end at infinity. But if I shift that lower index up by 1, then I have to take the expression and subtract 1 from n, which would just leave me with 1 over n. They have to basically go in opposite directions. And if you're not sure if you did that right, just list out the first few terms. So if n is 0, you would have 1 over 0 plus 1, so that's 1 over 1. If n is 1, then you'd have 1/2. If n is 2, you'd have 1/3. And then with the way I've shifted the indices now, starting with n equals 1, the first term is still 1, 1 over 1 plus 1/2 plus 1/3, etc. Well, do you recognize this series? Yes, that's the harmonic series. So we know, since this is the harmonic series and it diverges, then that tells me that x equals -1 is not an element of the interval of convergence, okay? So for sure I know this is not going to be an option and this is not going to be an option because my interval of convergence does not include -1. Well, what about +1? So let's let x equal +1. So what does the series look like now? We're going to have the sum n equals 0 to infinity. Remember, it's -1 to the n times x to the n, so it's going to be 1 to the n over n plus 1. Well, the 1 to the n isn't going to do anything, so I still have the sum n equals 0 to infinity of -1 to the n over n plus 1. Well, this looks like a good time to use the alternating series test. So let's use the AST. And remember, b sub n is equal to the absolute value of a sub n, which is going to be 1 over n plus 1. So condition 1, I need to show that it's decreasing. B sub n is decreasing. So b sub n plus 1 would be 1 over n plus 1 plus 1, so n plus 2. And that's for sure less than 1 over n plus 1 since the denominator is larger, which was bn. So first condition satisfied. And then second condition, I need to check that the limit as n approaches infinity of b sub n, so 1 over n plus 1, that it's 0. It sure is. So what does this mean? Well, this means that the sum n equals 0 to infinity of -1 to the n over n plus 1 converges by the alternating series test, which tells me what about x equals 1? Well, x equals 1 is part of my interval of convergence. So now I want to write out the final result for my interval of convergence. It does not include -1, but it does include +1. Okay, so you can see that testing for the radius and interval of convergence will require you to recall all of the other tests that we've considered so far. Good, let's move on to another example here. Example 2, find the radius of convergence and interval of convergence for the sum n equals 0 to infinity of n raised to the n times x to the n. Well, when I see n being raised to the n, that seems like a good time to use the root test. Remember, for finding the radius and interval of convergence, most likely you'll either use the ratio or the root test. So let's use the root test. And we'll have the limit as n approaches infinity of the nth root of, now remember we need the absolute value of the terms, so absolute value of n to the n times x to the n. Okay, so this is going to give us the limit as n approaches infinity. Now if I take the nth root of n to the n, I'm just going to get back n. But if I take the nth root of, remember, the absolute value of x to the n, x could be any real number. So I need to keep the absolute value bars around x. And this is the limit as n approaches infinity. So in this limit, x is not changing. So I can pull it outside of the limit. So I have absolute value of x times the limit as n approaches infinity of n. Well, you guys, no matter what I do, n is going to infinity, right? So this limit is blowing up. In fact, it's going to be less than 1 only when x is exactly equal to 0. If x is equal to anything other than 0, this limit will be infinity. So what does that mean? My radius of convergence is equal to 0, and my interval convergence is actually just a set with one lonely number, 0. Okay, good. Moving on, let's look at another example. Example 3, find the radius of convergence and the interval of convergence. So we have the sum n equals 0 to infinity, -1 to the n, times x to the 2n over 2n factorial. So which test do you think we should use? There's something that's giving me a clue. Yes, it's the factorial, so we want to use the ratio test. So we're going to look at the limit as n approaches infinity of the absolute value, I'm going to have a sub n plus 1, so negative 1 to the n plus 1 times x to the 2 times n plus 1. Be careful, put those parentheses in there. And then now also this is going to be 2 times n plus 1 factorial. Yes? Over negative 1 to the n times x to the 2n over 2n factorial. Okay, now we have to clean up with some care. So this is going to be the limit as n approaches infinity. Now negative 1 to the n plus 1, negative 1 to the n, that's all gone. Up here, let's look. This is going to be 2n plus 2, right? If I distributed the 2, so I can rewrite that as x to the 2n times x squared. And then similarly, I have 2n plus 2 factorial. So that means I have 2n plus 2 times 2n plus 1. And then now I'm going to leave it as 2n factorial because I know I have a 2n factorial sitting on the other side of the expression. And then times, let's see, that 2n factorial now is going to flip up to the numerator here. And then I have x to the 2n in the denominator still. Okay, and keep those absolute value bars. Now we get to have some fun and cancel away. So 2n factorial, that's gone. X to the 2n, that's gone. And x is squared in this case, so I'm fine if I don't put absolute value bars around it. We're going to have the limit as n approaches infinity of x squared times, and then I have 1 over 2n plus 2 times 2n plus 1 left over. Now let's look here. As n approaches infinity, the denominator here is getting larger and larger, and the numerator is just a constant. So this whole term is going to 0. And remember, in this limit, x squared is a constant. So I have x squared times 0. That means this limit is equal to 0. So regardless of what x is, this limit will equal 0, and 0 is always less than 1. And we require, by the root test, that this limit be strictly less than 1 in order for the series to converge. So what does that mean? This limit will always be less than 1. It will always satisfy the conditions of the ratio test. I'm sorry if I said root test earlier. It's always going to be less than 1, regardless of what I substitute in for x, so x can be anything. So that means the radius of convergence is infinite, and the interval of convergence is from negative infinity to infinity. I actually love when this happens, because then you don't have to bother checking the endpoints, right? Good. All right, one last example. Let's look at an infinite series where it's not centered at 0, right? We gotta take things to the next level. So find the radius of convergence and the interval of convergence. We have the sum n equals 0 to infinity times x minus 3 to the n over n to the 7th plus 1. So let's go ahead and use the ratio test this time again. So we have the limit as n approaches infinity of the absolute value of, I'll have x minus 3 to the n plus 1 over n plus 1 to the 7th plus 1 over x minus 3 to the n over n to the 7th plus 1. Okay, so let's see how we can clean things up. I'm going to have the limit as n approaches infinity, absolute value, x minus 3 to the n plus 1. Let me write that as x minus 3 to the n times x minus 3 over, and then n plus 1 to the 7th plus 1. I'm just going to leave it like that for now. Times, now I have n to the 7th plus 1 on the numerator and x minus 3 to the n in the denominator there. Okay, anything you notice I can cancel? I can cancel out x minus 3 to the n, that's good. okay? And then I'm just going to take out this x minus 3, but keep the absolute value outside of the limit. So I can just focus on everything with an n in it for the time being. So now we're going to have absolute value of x minus 3 times the limit as n approaches infinity. I'm going to have n to the 7th plus 1 over n plus 1 to the 7th plus 1. Now again, you have to be a little careful when you take this limit, because I am going to divide by the highest power of n in the denominator by 1 over n to the 7th. But now I have to be careful when I distribute it across. So this is going to be, let's rewrite what we have so far. So I have absolute value x minus 3 times the limit as n approaches infinity. Okay, in the numerator, when I distribute, I'm going to have n to the 7th over n to the 7th, so that's 1, plus 1 over n to the 7th. But then now, look, be careful. So when I put 1 over n to the 7th, inside the parentheses here, I'm going to have to take the 7th root, so it's just basically going to be dividing by n inside those parentheses. So I'm going to have 1 plus 1 over n to the 7th plus, and then now this is going to give me 1 over n to the 7th. Okay? All right, now let's see. Can we take this limit? So in the numerator, I just have the limit n approaches infinity. 1 is 1. 1 over n to the 7th, that's going to go to 0. 1 over n in the denominator, that goes to 0. So 1 plus 1 over n to the 7th, that's going to approach 1. And then 1 over n to the 7th, that also goes to 0. So I have a 1 in the numerator, and I have a 1 in the denominator, and I still have x minus 3 hanging outside. So this is equal to absolute value of x minus 3 times, what was that limit? It was just 1. Okay, this means here, this x minus 3, that in this case it's centered, right? My series is centered at 3. And remember, when we apply the ratio test, I would like for this limit to be less than 1, right? So we require this to be less than 1 to converge. Which means basically that the absolute value of x minus 3 has to be less than 1. So whatever number is over here, that's your radius of convergence. So my radius of convergence is still 1. But you might be wondering, well, what does it mean that it's centered at 3? Well, basically it means on your number line, here's 3, that's where it's centered, and the radius of convergence is 1. So you could go down to 2 or up to 4. I just need to figure out if I can include the endpoints or not, right? If I can include 2 or 4, but that radius is still 1. So our next task, what we need to do is we need to check the endpoints 2 and 4. Okay, so we have to do a test for each one of them. Our endpoints, let's start with x equaling 2. And remember, our series was the sum n equals 0 to infinity of x minus 3 to the n over n to the 7th plus 1. So if x is equal to 2, then we're going to have the sum n equals 0 to infinity 2 minus 3 to the n over n to the 7th plus 1. So this is going to give us the sum n equals 0 to infinity. We're going to have negative 1 to the n over n to the 7th plus 1. All right, so let's use the alternating series test. And Bn would be 1 over n to the 7th plus 1. So first thing I want to show is b sub n plus 1. That would be 1 over n plus 1 to the 7th plus 1. Is that less than 1 over n to the 7th plus 1? Well, for sure, right? The denominator got larger, so the whole expression is getting smaller. so I can show that it's decreasing. And the second thing that I want to be able to show is that the limit as n approaches infinity of bn, which is 1 over n to the 7th plus 1, that's 0, which it is. So what does this tell me? Then I know that the sum, n equals 0 to infinity of negative 1 to the n over n to the 7th plus 1 converges by the alternating series test. So x equals 2 is an element, or it belongs to the interval of convergence. All right, one endpoint down, one to go. So now we're going to check x equals 4. So let x equal 4. All right, so then we're going to have the sum, n equals 0 to infinity. Remember, it was x minus 3 to the n over n to the 7th plus 1. So this is the sum, n equals 0 to infinity, 4 minus 3 to the n over n to the 7th plus 1. Well, in the numerator, I'm just going to have 1 to the n, which is always 1. So I don't even need to write it. So I have the sum, n equals 0 to infinity, just leave it as 1, over n to the 7th plus 1. All right. Now, what do we want to do? What do we feel is going on with this series to begin with? Well, I notice there's n to the 7th, so it's growing pretty fast. It reminds me of the p series, 1 over n to the 7th. And since there's that plus 1, I could actually just use direct comparison instead of dealing with a limit comparison test. However, my index is starting at 0, so I have to be careful there. So I'm just going to consider the sum. Let's start at 1 to infinity of 1 over n to the 7th plus 1. Okay. And recall that the sum, n equals 1 to infinity of 1 over n to the 7th converges. You have to state how you know that. Well, it's a p series, and p equals 7, which is greater than 1. And then clearly we can see that 1 over n to the 7th plus 1 is strictly less than 1 over n to the 7th. So this means that the sum, n equals 1 to infinity, of 1 over n to the 7th plus 1 converges by direct comparison. Okay, but you might be worried. Remember, our series started at 0, not at 1. But think about it. If your infinite series converges and I just add in one more term, is that going to harm or change the fact that it converges? No, you're just adding in one more term. That's a finite number of terms, so that's no problem. So you have to state, though, that you've thought about such a thing. So this means that the sum, n equals 0 to infinity of 1 over n to the 7th plus 1 converges also. And then what does that tell me? Well, now I know that x equals 4 also belongs to the interval of convergence. So the final part of my solution is to write out what that interval of convergence is. It's going to be a closed interval, including both endpoints 2 and 4. All right, so that concludes the examples. Be sure to like and subscribe and leave a comment down below for what other videos and sorts of things you'd like to see next.